Okay, this is Leetcode 3092, most frequent IDs. So we're given two integer arrays of equal length, nums and frequency, where nums represents the ID number or primary key, and frequency represents the frequency count that we need to add or subtract from that particular ID at a given point in time. We are tasked with then returning a answer array of length n that represents the max frequency count at each interval. So the very naive way to go about this would be we have some dictionary, and what we would do is we would map each ID number to the frequency count, and at each step we would take the max of that and add that to our answer array. And I will quickly walk through, using this test case, just this solution. So at the first interval, we know we have a ID value of 2. We can add this to our dictionary with a frequency of 3. And at this step, we can then add 3 to our answer array, because the max we could just take the max of the dictionary, the values in the dictionary, that's 3. Now, when we go to, as we go to our next value in nums, or our next ID in nums, we can then add 3 with a frequency value of 2 to our dictionary, and we take the max again of the dictionary. So the max here would still be 3. Now, our next step, we go to ID of 2 again, and now we get to -3. What we need to do here is go look in our dictionary, see if 2 has already been used, which it has, and then we need to go subtract that by 3. This leaves us with 0, and then we take the max of the frequency values, which would now be 2. And then finally, we get to 1, and we need to then add a new value to the dictionary with a frequency count of 1. And we can take the max value again. The max value again is 2, which is our answer right down here. Now, the problem with this is we are going through nums n times, but then we are also calculating the max that's in the dictionary, which could be up to n. There could be n values in the dictionary. We're going to have to do that. We're going to have to look through n values. So if we're looping through n times and we have to look through n values at each step, we have an n squared time complexity, which obviously isn't ideal, and we need to ask ourselves if we can do better, which we can. Okay, why can't we just go through and have a max num variable, and effectively each time we go through a different frequency, we can either choose to update or not update this max num, and that can be whatever our answer is at that particular point in time in our answer array. And I'll walk through quickly why this wouldn't work. And the reason it doesn't work is we will, after the first iteration, we'll have a 3 here, and we can add this 3 to our array. Then we'll compare a 2 to the 3. The 3 is obviously greater. We'll have the 3 here, and here is where it breaks down. The reason it breaks down is because we can obviously have multiple ID numbers in nums. So we can effectively change the value, subtract or add different values to our ID, to our same ID number. And we know at this point that we can't simply just, even if we were able to store this connection, we can't just simply, we can't return 3 here, that's wrong. We can't then subtract this by 3 and return 0, that's wrong as well. We need to effectively return 2, which we have no way of getting back to 2, given if we have n numbers. So how we're going to have to go about doing this is we're going to have to store our numbers in a way that allows us to grab that next greatest frequency count. And the light bulb should be going off in people's heads that the best way to do that is using a max heap. And how we're going to do this is we're going to go through our array and we are going to push the frequency count with the number, with the ID number to our max heap. And at each step, we're going to take the top value and add that to our answer array at each iteration. So as we go through nums and frequency here, after our first step, we'll have 3, which is mapped to 2. And we'll take the top of the max heap, which we know we can do that in O of 1 time. And the top of the max heap would be 3. And then we can add our next value. We can add 2 as our frequency and 3 as our ID. Take the max heap at this point. The max heap is still 3. Now is where we reach our edge case. And our edge case tells us that, okay, the value 2 here, or the ID 2 here, we need to subtract that by 3. So when we look at our top value in our max heap, we know that this is a frequency 3, and we effectively know we need to pop this value, and we need to subtract 3 by the value here. And then the next top value in our heap is 2, and we can add 2 to here. And this would work, but the one scenario that this would fail on is if the value that we are trying to change, so if -3 comes up, if that value is not at the top of our heap, we know we have a problem. And the problem is pushing to a heap is log n time, popping from a heap is log n time. But removing a value from a given point in the heap or a random point in the heap is a no-no because it breaks the entire structure of the heap. So that's where, if you aren't creative, that's where it's pretty hard to keep going with this approach and this problem. And what I'm going to do is we're still going to use a max heap, but we're going to bring back something that we had at the start, which is a dictionary. And we're going to use the dictionary to, at each step, we are going to add to our key values what the new frequency would be at each step. And we're going to then compare, when we have our top value to the heap, we're going to compare whether that's the value we have in the dictionary. So there's a reason these are called bookkeeping problems, because this is exactly what we're doing. We're effectively ensuring that our frequency count actually matches the real frequency count and still returning the max value efficiently. So one more time as we go through this, we'll keep the max heap the same because nothing's going to change here, but we are going to add in to our dictionary the value 3, so, and the ID 2. So 2 maps to 3, and then we're going to also add in the ID of 3, which maps to 2. And when we reach this point, what we're going to do is we're going to go into our dictionary and we are going to change. We're going to change this value. So we're going to subtract, because we can look up, we can do lookups in constant time with a dictionary. We can efficiently look up whatever key this is, 2, and we can subtract 3 from this value. 2 now becomes 0 in constant time in our dictionary. And when we look at our top value in the max heap, we're going to find that it's 3, 2. So our value is 3, our ID is 2. We are then going to check in our dictionary and ensure that that is truly what the value should be. And after that, if it is, we will keep this in the heap. If it's not, what we're going to do is we're going to pop this value from the heap. And then we're going to look at our next value, which our next greatest value is 2. We're then going to check, is that what ID 3 really is in our dictionary? Yes, ID 3 is 2. We can then add 2 to our answer array. And before we think that we're probably done with this point, what we then need to do is we then need to push onto our heap. So we've gotten rid of this. We then need to push onto our heap the new updated value. And the new updated value would be 0 with an ID of 2. And this is our efficient solution, and our time complexity for this is going to be n log n. And the reason is we're going to go through our input array n times. So we're going to loop through n times, and at each point we are going to have to push to our array. So that's pushing to our heap, and pushing to our heap is always log n. And we also might have to pop from our heap, so log n as well. And we obviously drop constants, so we end up at n log n time complexity, which is a big improvement on our naive n squared solution. Okay, let's get into the coding solution here. So we're going to initialize our heap to a dynamic array. Obviously, a heap is a abstract data type, so we can represent it with a multitude of different data structures. Obviously, the easiest and most common being a dynamic array. A tree is also used, but we're going to use a dynamic array. Then we're going to initialize our dictionary to an empty hash map, or dict in Python. And what we're going to need to then do is we're going to then need to loop through or zip through nums and frequency. So a convenient way of doing this in Python is using the zip keyword. And we're going to grab the ID, and we're going to call the frequency f in zip nums frequency. And what we're going to need to do first we're going to need to update our dictionary. So our dictionary value could be empty for each ID, or it could contain a value. So in order to do that, we're going to index in to our dictionary, to our ID of our dictionary, and we're going to need to use the get command here to grab whatever that value is, so we can increment or decrement it as needed. And this value could be 0, so we're going to use ID here, and it could be 0, so we're going to set that equal to 0, being our default if it is an empty dictionary or the value is empty, and we're going to increment that by f. So whatever f is, if f is negative, it'll obviously subtract. So f's our frequency. So this line should do a very good job of bookkeeping and keeping track of whatever the value of dictionary is at that current point in time, or whatever the value of the ID in the dictionary is at that current point in time. So next, what we're going to need to do is we're going to need to push onto the heap. And the one thing that we need to remember is we need to remember that in order to keep the sorted order of the heap, we're going to need to lead with our frequency value, and we're going to need to include our ID value for bookkeeping purposes later on when we attempt to pop from the heap and check and see if that value is what that value really is in our dictionary. And the next thing that we need to remember is that Python does not support a native native max heap. It only supports a native min heap. So how we're going to need to do that is we're going to need to makeshift our min heap into a max heap, and the easiest way to do that is by multiplying by -1, or in essence taking the inverse of each number, which just represents a max heap using a min heap. So how we're going to do that is we're going to push in a list so we can index into it, and the first value is going to be whatever is our dictionary ID. So don't put in the frequency value because that could be wrong at that point. What we're going to need to do is we're going to need to index into our dictionary, grab the ID number of that, and remember we're going to need to multiply that by -1. And our second value that we're going to add is our ID number, or our ID value. And this should maintain the sorted order and allow us to easily access what the greatest value is in each iteration. So next, we're going to set up a while loop. And usually with heap problems, we have to set this condition first, while heap. And in this problem, we actually don't need to do that. And the reason being is because we could never have, even though we're popping from the heap, we can never have less than one value in the heap. So we will always be able to, this will never be like an index out of bounds. If we try and index into an empty heap, we don't have to worry about this condition for this problem. But what we are going to set is we're going to continue this while loop while the value in the dictionary for whatever the top of the heap is different from what the top of the heap, the value is in the top of the heap. And because what this loop is going to do is we're going to pop from the heap and we're going to remove values that are no longer valid as our max value. And whenever we exit out of this while loop, we know that the top of the heap, the value of the top of the heap is the correct top value, so we can just add that to our answer array. And the one thing I forgot to do is actually add an answer array up here, initialize this answer array. So the code for this would be while the dictionary, and it's going to be equal to the value. So this is the top of the heap 0. And what we're going to need to grab is we're going to need to grab the ID of, the ID of that number at heap 0, and we're going to put that into our dictionary and see what value that is. And we're going to compare that value. So while that value is not equal to whatever the value is at the top of the heap, and remember, we're going to need to multiply this by -1 because we are representing this as a max heap. And while that's the case, what we can do is we can just pop from the heap. And this will get us to a point where all we now need to do is we just need to append the top value on the heap. the top frequency of the top value on the heap. And the one thing we need to remember is we need to remember to multiply that by -1. And this here should be the right answer. We'll run this. And there we go, accepted. So